Okay, this application I want to take a look at with system of linear equations is network analysis. So this is a very broad application. Networks are composed mathematically of what we call branches and nodes or junctions through which something flows. We use them to model things like electrical networks, traffic flow, drainage and water supply systems, production and consumption processes. We can be modeling, for instance, for traffic, the branches may be roads, and the flow would be the vehicular traffic there. The nodes would be like street intersections. Other models could be, the branches being the connection between different, say, shipping offices for a shipping company, and all the nodes are where the packages get transferred to. So we're looking for the flow rate of packages through the network. The common concept in all these models is the total flow, be it electrical current, traffic, water, manufactured goods, packages, whatever's flowing through our branches there, that flow into any node is equal to the flow out of the node. So flow conservation. So we won't have accumulation of flow at each node in this analysis we're going to do. So for example, in the diagram below, I'm going to use circles to represent nodes. So this could be a location, street intersection, could be a location of our where we're a shipping facility, whatever it is. We have then flow rates represented by arrows. So this node has 35 units flowing out. This could be whatever our units are: electrical current, traffic, and vehicles per hour or vehicles per minute or whatever the rate is, packages per hour, whatever it is. And then we have two unknown quantities, and that's where we'll have unknowns, right? X of 1, X of 2 coming in. Okay, and these could be coming from different, maybe this is packaging different facilities. So since we have conservation of flow, that means when I add the incoming flows, right, that has to equal what comes out. We can't have any accumulation, so what comes in has to go out. So you have that equation. And what we're going to do is, for the system, we're going to have lots of nodes, and for each node we'll have an equation. Okay. Since each node can be represented by a linear equation, then we get a system of linear equations when we have a network composed of more than one node. So here's an example. We're going to set up and solve this network, and this is a network of water pipe. So we have water flowing through these pipes where the arrows are going, and the circles are the nodes where the pipes intersect. Okay, so just a simple little example here. This question in this case, what will all the flow rates be if the water is shut off between nodes 5 and 1? We'll answer that after we do the analysis and come up with everything. Here's node 1 and 5, and you can see the X of 5 is that flow rate. You could actually solve this whole problem very easily by letting that be 0, and you can trickle through this. The object, though, of this is not to just do that here, but to show how we would set this up. Then if you have a system where you have hundreds of nodes, you would not want to manually go through and do all that. You would have the software to solve that system, and I want you to be able to set up that system. And so the key here is I'm going to look at each node. I've got 5 nodes, and again, remember the input has to equal the output, and that's the way I'm going to do all my setups here. So that's the way all of this will proceed. Keep it organized in a sense. So in node 1, what do I have going in? Well, these flow rates. Now, one thing about flow rates, let me just say this. I've got x1, right, going obviously from node 1 to node 2, and I get x5 going from node 5 to node 1. How do I know? X1 and X5 are unknown node rates. How do I know which way they're flowing? Okay. Well, here's the thing. You may not. If you don't know the flow rate between node 1 and node 2, just go ahead and draw a direction like I've done here and label that variable x of 1. Now, if I solve this system and I get x of 1 to be, say, positive 2, maybe the flow rate is cubic feet per minute, 2 cubic feet per minute. If it's positive 2, then you've got the right direction. If it comes out to be negative 2, what does that mean? It means you've got the wrong direction. You need to change in the other direction. So that's how it will play out if you don't know the direction. Just pick a direction If the value of your variable in that situation then is positive, then you've chosen the correct direction. If negative, it's the opposite direction. So node 1, I've set it up. What's going in? I've got x of 5 going in, so I'm going to put that on the left, equals what's going out. What's going out is x of 1 plus 20, right, going from node 1 to node 4. Now, that's the equation from that node, but I'm going to rewrite it in the form I need for the system of linear equations. When we plug it in and get the augmented matrix, I want to have all the variables on the left-hand side, so I'm going to subtract the x of 1. And I like to put, the variables in order from 1 to 5 here. So I'll put them in that order and leave the constant on the right-hand side. So there I just subtracted x of 1. So let's continue with node 2. Node 2, we have coming in, we have x1 plus 30. And going out, we have x of 2. Again, I want to get the x of 2 over there. That constant term I want to get on the right, so I'm going to subtract x of 2 from both sides, and I'm going to subtract 30 from both sides. There's my second equation. Node 3, I've got x of 2 coming in, and what's going out? X of 3 plus 10. Again, subtract x of 3. My third equation. 2 more nodes to go. Node 4, I've got x of 3 plus 20 going in. What's flowing out? X of 4. So I'm going to subtract x of 4 and subtract 20 from both sides so I can get it in this form. X of 3 minus x of 4. Subtract 20 from both sides. I get negative 20 there. So be careful, a lot of mistakes can be made in this very simple getting this in the right form. The last node, 5. I've got going in x of 4 plus 10, and what's coming out? X of 5 plus 30. And so I'm going to subtract x of 5 and subtract the 10. Right, so I get x of 4 minus x of 5. When I subtract 10 from 30, that's going to leave me 20. Okay, so this right here on the right, then this is my system of what? 5 equations in 5 unknowns. And I want to be able to solve that system, so I'm going to write the augmented matrix for that system. Do that on a separate sheet of paper here. Okay. Now, what happens a lot of times with these type of network systems, because only certain flow rates are connected to particular nodes, get very what we call sparse matrix. There's going to be a lot of zeros in it. In fact, the first equation, what's it look like? There's the coefficient of x of 1 is negative 1, so I'm going to start with negative 1 there. And then x of 2, x of 3, x of 4 all have zeros. So x of 2, x of 3, x of 4 all have zeros. X of 5 has a 1 equals 20. There's my first row, and you see a lot of zeros in that. Right? See a lot of zeros in that. For the second equation, I've got 1x of 1 minus 1x of 2, no x of 3, x of 4, x of 5, so I've got negative 30 for my constant. Right? And so we continue to proceed through that. The next equation has no x of 1, 1x of 2, minus x of 3, no x of 4, no x of 5, equals 10, and so on. And then the last, x of 4, 2, 3, x of 4, minus x of 5 equals 20. We're going to put parentheses or brackets, as you should always, for a matrix. Right? And so there's our augmented matrix, and it's very sparse. There's obviously a little pattern you see developed in here. And it's actually, you think about what we want to do with this now is what we want to put this into reducer echelon form. And when you do that, you see like it's pretty close, right? I mean, it's like we almost got leading ones, but we obviously don't have a leading one in this first row, so we've got to do a little work there. Again, you don't have to manually do the Gauss-Jordan elimination. You can use technology to put this matrix into reducer echelon form. In the last video, when we were doing the interpolating polynomial, I showed you how to do that. So I would like you to enter this matrix into your calculator and go ahead and put it in reduced echelon form and confirm that this is what you get. The fifth column is a little different, interestingly enough, and then our last column looks like this. Now, okay, so confirm that that's what you got, and this is, notice our leading ones. We've got a leading one here, leading one here, leading one here, leading one here, so that corresponds to x of 1, x of 2, x of 3, x of 4. Those are fixed variables. And notice here, x of 5 does not have a leading 1. There's no leading 1. So x of 5 is a free variable. So what's that mean? Notice our last equation has 0 equals 0. This system is consistent. This means what? That we have infinitely many solutions. Right? So when we do that, we want to parameterize. So I'm going to let x of 5 be the parameter. We'll choose t, and we can now write out our solution based on that. So let's do that. From the first equation, and again, it doesn't look too much different from what we started with, but the first equation is x of 1 minus x of 5 equals negative 20. But x of 1 is a fixed variable. X of 5 is a free variable. We want to solve our fixed variables in terms of the free variables. So if I solve for x of 1, I add x of 5. And that's going to be x of 5, which is actually t minus 20. Right? If I add x of 5 that side. So I want to put this in terms of t. The second equation is x of 2 minus x of 5 equals 10. And again, I add the x of 5, which is t, and I get x of 2 is t plus 10. Third equation, x of 3. And this is equal to 0. So if I add x of 5, I get x of 3 is equal to x of 5, but I'm going to write t for x of 5 again. Then x of 4 minus x of 5 equals 20. Again, add x of 5 or t, I get x of 4 is t plus 20. And then I'm just going to go ahead and in my solution, I like to do this, so you want to just rewrite it, x of 5 again is t. So this has all my variables, x1 through x sub 5. And this is really the way you would write out your solution in parameterized form. This is our solution. Okay. Infinitely many solutions. And that happens a lot of times when you're doing these network analysis. Okay, so now what we look at is go back to the question. The question was, what if we shut off that flow rate from x node 5 to node 1? That's x of 5 gets shut off. That means x of 5 goes to 0. How is everything else affected? Well, now that we have the general solution, I can find that particular solution, right? X of 5 is 0, or of course our parameter t being 0. What do we get? We just plug in 0 for t, we get negative 20. X of 2 is 10, x of 3 is 0, x of 4 is 10, and I'll just go ahead and say x of 5 again is 0. So there's our specific solution there. A couple things to note. X of 1 is negative 20, so remember what we said, and we'll go back to the picture. That means in the case where x of 5 is 0, we shut off the flow rate between these two nodes, then the flow rate has to be going in this direction, right? Instead of going from node 1 to node 2, it's going from node 2 to node 1. And also the flow rate x of 3, also notice that goes to 0 when we do that. So this is, very simple system. And again, you could have deduced this by just simply saying, okay, if I let that be 0, well now I've got 20 coming out, so I have to have what? 20 coming in. So x of 1 has got to be 20 and going in the opposite direction. So it's negative 20. And once you have 20 coming out of node 2 now and 30 going in, right, that's a net of what? 10 left over that has to be flowing out. So you can work your way through that and you can answer the question. But again, if you have a network that has hundreds of nodes, you're going to have obviously a computer program to solve that system of linear equations for you, and you would know how to set it up though. And so this is a neat little thing. Again, network analysis, lots of application there. And this just hits the tip of the iceberg. There's much more to look at for network analysis and more complicated things, especially if you begin to talk about accumulation at nodes. It gets a little more complicated, but at the base level, this is a very nice application. Okay. The next application we're going to look at is actually a new method for solving systems of linear equations known as the Lu Decomposition Method. So we'll be looking at that in the next video.